So yeah, thanks very much for the invitation and for the opportunity to talk about this material. Today I want to give you an idea of what is a rigid geometric structure, basically telling you what is a G structure of finite type. And the reference for what I'm talking about today is the book by Shoshichi Kobayashi. And then next time I'll tell you a bit about Gromov's generalization of this notion and about groups acting on rigid geometric structures. So to start, let me show you some examples and non-examples of rigid geometric structures. Okay, so the first example is or I'll take here for the whole time, M is a manifold, a smooth manifold. And the first example is a Riemannian metric on M. This is a rigid geometric structure. Okay? And a manifestation of that is the following theorem due to Myers and Steenrod. From 1939. Okay, it says that the isometry group of any Riemannian metric on any manifold is a Lie group. In the compact open topology. Okay. And they proved, moreover, that for each x, the isotropy is compact and that if M is compact, then the whole isotropy group is compact. Sorry, the whole isometry group. Okay, yes?
What are you assuming about the regularity of G here?
Smooth? Everything's smooth.
Everything's smooth?
Yeah.
You're talking?
C infinity is, yeah. Okay, so, and in fact, it turns out for any kind of semi-Riemannian metric, that is, for any non-degenerate symmetric bilinear form on the tangent bundle of a manifold, the isometry group is a Lie group in the compact open topology. These second compactness statements are not true in higher signature, but we'll eventually see how these can be deduced from the rigidity of a Riemannian metric in the point of view that I want to show you. Okay. So that's an example. So Riemannian metrics, and in fact, semi-Riemannian metrics, that is, non-degenerate symmetric bilinear forms on the tangent bundle. By contrast, if you take a skew-symmetric non-degenerate bilinear form, and let's say add the condition that it corresponds to a closed two form, then it's not a rigid geometric structure. So this is a skew-symmetric, non-degenerate, bilinear form on Tm, satisfying the additional assumption that it's closed. Okay, so that's commonly known as a symplectic structure. This is not rigid. Okay, and I haven't told you what rigid means. That's the goal of this lecture. But here's a manifestation of that. So this is a theorem due to Lieberman from 1959. So if we look at the infinitesimal symplectomorphisms, namely if we consider the vector fields, so this is going to be my notation for the infinitesimal symplectomorphisms on M. So these are the vector fields on M which infinitesimally preserve omega, meaning that the Lie derivative of omega with respect to x is 0. Okay? So this can be identified with the closed one forms on M. So with the set of nu in omega 1 M, so that g nu equals 0. Okay, so this is the infinitesimal version of the isometry group for a symplectic structure, and what I'm telling you is that it's huge. Okay. And
Sam was saying that the flow, like the field is preserving the form?
yes.
That's the same thing?
Yes. Okay. But the flow, I mean, technically speaking, I'm not assuming that it's complete, so that's a local statement around each point. Yeah. Okay, and this I can actually prove. So Lx omega by Cartan's so-called magic formula is Ix. So this is what you get if you insert x into omega. This corresponds to inserting x into omega, composed with exterior derivative plus exterior derivative composed with Ix of omega. By the assumption that omega is closed, this term is 0. So this is d Ix omega. Okay? So Lx omega, the Lie derivative of omega with respect to x, is 0 if and only if the one form Ix omega is closed. However, omega is non-degenerate. So if I have one of these infinitesimal symplectomorphisms, it gives me a closed one form, but conversely, any closed one form gives me a vector field x, thanks to omega. Okay? So this says that, so any x gives me that Ix omega is a closed one form. Okay, but conversely, if I have a closed one form, then nu of y equals omega xy for all y determines a unique x because omega is non-degenerate. Okay, so I'll show one more example and one more non-example. So now I'll take the conformal class of a Riemannian metric. So this is all of the metrics which can be obtained from an initial Riemannian metric by multiplication with a smooth function. Okay. So what this corresponds to, if G is a Riemannian metric, is a well-defined notion of angle measurements, but not a well-defined notion of length measurements on a manifold. Okay, so this is a conformal structure. Okay. And the theorem, which is basically due to Cartan from 1923, not 2023, is, sorry, I will also want to credit Palais for this particular interpretation, is that if n, the dimension of M, is at least 3, then the conformal group of M, so these are the diffeos which preserve the conformal class of G. This is a Lie group of dimension at most n plus 1 times n plus 2 over 2. And for comparison, the maximum dimension of the isometry group is n times n plus 1 over 2. And by contrast, a non-example is a complex structure on an even dimensional manifold. Okay, so this consists of a field of endomorphisms that corresponds to multiplication by I and satisfying an additional integrability condition. So this is called an almost complex structure, just such a field of endomorphisms. But if one wants to obtain from this an atlas of charts to CK so that the transitions are holomorphic, there's an integrability condition which is given by the Nienhuis tensor. Then this is a geometric structure which is not rigid. And one way to see that this is not rigid, again, without me having defined for you precisely what rigid means, but what you can see is this finite dimensionality of the automorphisms here versus infinite dimensionality of the automorphisms for the non-examples. And the manifestation that one can see here is if we just look at local automorphisms of a complex structure. So local automorphisms of such a structure are just local biholomorphisms from a neighborhood to itself. Okay, and evidently this is infinite dimensional. So well, let me finish what I wanted to say. So basically, a local biholomorphism is just given by any invertible and convergent Taylor series in Z around the origin. Okay, so any convergent and invertible Taylor series in Z1, ZK. Okay. And some of you might say, wait a minute, on a complex, on a compact complex manifold, the automorphisms are a finite dimensional Lie group, but that's a strictly global phenomenon. And being a rigid geometric structure is something which is characterized locally. Okay. So these are not rigid geometric structures. And the reason that I juxtapose these two is that in dimension 2, they're actually the same thing. Okay, so note, these are actually the same thing. And for people who aren't familiar with that, I'll maybe put it in the exercises. Okay. Are there any questions at this point? So this is, well, there are probably a lot of questions actually, because I haven't been very precise yet. So, so now I want to show you something a bit more precise. Okay, I think I'll do it over here. Okay, so now I want to focus on Riemannian metrics and why they're rigid. Okay, so are there any questions? Okay. The key to the rigidity of Riemannian metrics is the existence of the Levi-Civita connection. So given G, there exists a unique connection which is torsion-free and compatible with the metric. Okay. And one way to see this is with the famous Kosu formula. Right? So we can just write down exactly what this connection has to be. In terms of quantities that are determined by the metric. Okay, so plus x, y, z plus y, z, x. Okay, so this is something one sees in a first course on Riemannian geometry, and now I want to show a different perspective on that. Okay? And this is called Cartan's lemma. Okay. And this is purely a lemma in multilinear algebra. Okay. And so it says the following. So if we're given omega 1 through omega n some linear forms on Rn, which are linearly independent. And given any two forms, mu 1 up to, or I'm calling them gamma 1 up to gamma n, there exists a unique collection of one forms so sorry, these are two forms. And these are one forms, but it's a family of one forms. Okay, so a priori it's a family of n squared one forms, but they satisfy the skew symmetry relation, so it's actually n times n minus 1 over 2 one forms, such that gamma I equals minus the sum of omega ij wedge omega j. Okay, so I'll indicate quickly why this is true, and then tell you what it has to do with that. Okay. So okay, so we'll write, so proof, we write gamma I as some combination of omega j wedge omega k. Okay, so that's possible because this is an arbitrary two form and these are linearly independent. Okay, so any two form can be expressed as a combination of these. And of course we have that aijk is minus aikj. Okay, and now I'll tell you how to define the omega ij's. So you just define omega ij to be minus the sum over k of aj ik plus ai kj minus ak ji omega k. Okay, so I claim that now if you take this thing, you wedge it with omega j, and you sum over j as well, then what happens is that these two terms, because they have the skew symmetry down here, and then when you wedge with omega j, they'll have a skew symmetry in j and k, and they cancel out. Okay, I'm not going to go through the details. And you're left with what you wanted, which is ai kj omega k wedge omega j, which is gamma I. Okay. But I want to actually show you the uniqueness. Okay. So suppose that we had two omega ij's, two families of these one forms that give us the same thing. So then we would have that they're different, so we can take their difference and wedge with omega j and add it up. And this would be 0. Okay? And and these we could write as, so let's let this difference so this is Bij k omega k, because again, these are just one forms. These omega i's span Rn star, so we can write this one form as some combination of those, and these are the coefficients. Okay? And so basically, this condition, the fact that when you wedge it with omega j, that you get 0, this implies that Bij jk equals Bijkj. Okay? But on the other hand, we had this skew symmetry here in I and j. So we also know that Bijk is minus Bijik. Okay? And so then we do this little game. So here I'm going to show you the little game with the forms. Okay, so we have Bijk equals minus Bijik equals minus Bijki equals Bk Bijki equals Bk Ji, yeah, that's right, equals Bk Ij, and then I'll do one more switch, equals minus Bijkj equals minus Bijk. Okay, and believe it or not, that actually proves something. Okay, so this combination of symmetries that this difference has means that the coefficients are, they're negative, so it's 0. Okay? So that's the end of the Cartan lemma. So what does this have to do with the existence of the Levi-Civita connection? Okay? Well, we apply the Cartan lemma to gamma I equals d omega I. So we take omega I now, instead of being a linear form on Rn, we take a family of one forms on an open subset of Rn. Okay? So we take omega 1 up to omega n, some one forms on Rn or on an open subset of Rn. And so that they're linearly independent, and in fact, so that they correspond to an orthonormal framing for the metric. So I'll come back to that. Okay. And so what the Cartan lemma says is that there exists these unique omega ij's so that d omega I plus the sum of omega ij wedge omega j equals 0. And this is unique at each point. Okay, because what we proved here was just a fact about multilinear algebra in Rn. Okay, but as you might surmise, the uniqueness, or you don't even need to surmise it, you can look at the very explicit formula that we have here. If the omega i's are varying smoothly, then d omega i's are smooth, and the omega ij's will be smooth forms as well. Okay? So this existence and uniqueness point-wise tells you that actually if we take some locally defined smooth one forms, then we get some uniquely locally defined smooth one forms here. Okay? And so, good. So then what does that have to do with the Levi-Civitas connection? Again, okay, so the way to think about this is that these omega i's and the omega ij, so I think of this as a skew-symmetric matrix of one forms. So this is called a gauge. Okay, and so what it means is we have local orthonormal framing. So we take the omega i's, a local orthonormal framing for the metric. Okay, so that means that if we this gives us at each point an isomorphism of Rn, or sorry, of our tangent space. So omega 1 through omega n goes from Txm to Rn. Okay, so each of these one forms are giving the components of a vector. So this is at a point x in Rn. Okay, and these. It gives us then an isomorphism for each x because we took them to be linearly independent. Okay, and then if we take the standard Euclidean inner product on Rn and take an orthonormal basis for that, then that should correspond to an orthonormal basis for the metric at x. Okay, so these should be defining linear isometry from Txm with the metric Gx to Rn with the Euclidean inner product. Okay, so that's a local orthonormal framing. And so that defines a section of the orthonormal frame bundle. A local section of the orthonormal frame bundle, which is the bundle comprising points x and linear isometries theta from Txm to Rn. Okay, so what we have here is a smooth choice of isometries from the tangent spaces of M to Euclidean space. Okay. And now this, these omega ij's did correspond to a connection so the omega ij's are the pullback of forms on the orthonormal frame bundle by this section. Okay, so now I want to view the omega i's and the omega ij's on OM. So the omega i's can be viewed as forms on OM. So maybe I'll describe how I make that shift. So the omega i's are called the tautological one forms. Or also the soldering forms. So if we have a point of OM, so given V in the tangent space of this orthonormal frame bundle at a point Xi, so Xi corresponds to a linear isomorphism from a point of M, from the tangent space at a point of M to Rn. Okay? So these forms, so omega 1 of V up to omega n of V are what we get if we so Xi, my point is, I'll view it as a pair, a point of X and this linear isomorphism. So omega 1 through omega n of V is theta of d pi Xi of V. So maybe I'll make a picture. So here's M, here's X. Okay, here's the tangent space. And here's theta, this isomorphism to Rn, which is also a linear isometry for the metric. Okay. And then we have this bundle, OM. And here's this point Xi, which corresponds to X theta. Okay? So given a a tangent vector V here, what these tautological one forms do is project V to the tangent space and read them in the corresponding framing. Okay. And then let me tell you what the omega ij's are. Okay, so to explain the omega ij's, let me tell you more about this orthonormal frame bundle. So this is a principal ON bundle. What does that mean? It means that ON acts simply transitively on the fibers. By, well, G, let me not use G, H in ON acts by, if I have x theta, we typically write H acting on the right, then it's x H composed theta. Okay? So if theta was a linear isometry from the tangent space at x to Euclidean space to Rn, then this composition will be as well. And all of the linear isometries from a given tangent space to Rn correspond to, like, can be obtained from an initial one by this action. Okay? And so that means so that if we choose any initial point in a fiber, then we get a diffeomorphism from ON to the fiber. And in particular, if we take the differential at the identity of that diffeomorphism, we get an isomorphism between the tangent space to the fiber and the tangent space at the identity to the group. So this tangent space to the fiber I'll think of as the kernel of the differential, to be consistent with my notation. So this is pi, the projection from OM to M at the point C. So we get an identification that's quite natural between these tangent spaces to the fibers and the tangent spaces to the group, which is the Lie algebra, which in the case of ON is the space of skew-symmetric n by n matrices. Okay? And omega ij can be viewed as a one form taking values in this space of skew-symmetric matrices. And so what's the omega ij? Well, it turns out if you restrict it to the tangent space to the fiber, it's just this isomorphism. But the trick is, if you want to evaluate omega ij on the full tangent space to this bundle at Xi, you need a way to project to the fiber. And so the magical ingredient, the key ingredient, I should say, that these omega ij's are giving is their kernel determines a complement to the tangent space to the fiber. So omega ij restricted to this tangent space to the fiber, which I'm denoting like this, is this isomorphism, this one here. Okay, but the kernel of omega ij at a point C is this so-called horizontal space okay, which is a complement to the tangent space of the fiber. Okay, so this is a crash course in principal connections. And the relationship with the Levi-Civita connection is that if you want to parallel transport a frame along a curve, so here's the connection. So let's say that I have a curve alpha in M. Okay, so knowing the connection is the same as knowing parallel transport along all curves. Okay, so I'll start with a frame. Okay, and how do I parallel transport it along alpha? Well, I choose. So if I started with a frame, that means I'm starting with a point in the orthonormal frame bundle over X. Okay, and I have this horizontal distribution. And because alpha is a curve, there's a unique lift of alpha to this bundle, which is tangent to that horizontal distribution and passes through Xi. Okay, so I take alpha hat, which is a lift of alpha tangent to that horizontal distribution. And that exactly defines an orthonormal framing along alpha, and that's my parallel transport. Okay, so the corresponding orthonormal framing along alpha is the parallel transport. Okay, so again, that's a crash course in principal connections and what they have to do with covariant derivatives on the tangent bundle that you're more familiar with. And the reason that I'm showing you this is twofold. So first of all, this existence and uniqueness of the Levi-Civita connection corresponds to the existence and uniqueness of these one forms on OM, which actually give a framing of OM. Okay, so let me write down the moral, the two morals. Okay, so the upshot is that the existence and uniqueness of that Levi-Civita connection, which is torsion-free and compatible with the metric, corresponds to the existence and uniqueness of these forms on OM, which give a natural, and I'll say more next time about what I mean by natural, framing on OM. Okay, so what's a framing of OM? It's an isomorphism of each tangent space, well, in this case, with this vector space. Okay. And the second upshot is that what made all of this work was this purely multilinear algebraic calculation. So in Cartan's lemma, okay, and in the last few minutes, I'm going to make some definitions that capture what happened in Cartan's lemma. Okay. So maybe I will raise this one. Well, I'll spend the last the first of my last few minutes in rearranging the boards. And then I'll spend my last, oops. No, not that one. This one. Here it comes. Okay. And then I'll spend my last, n minus 5 minutes telling you. Okay. Okay, so here's the definition. Given G, Lie algebra in GLNR. So in other words, a subalgebra of the n by n matrices. We define the kth prolongation of G so this is the set of lambda, which are symmetric K-forms with values in Rn, having the property that if we plug in to K minus 1 spots, so we take lambda of V1 up to Vk, then we get an endomorphism of Rn, and this should belong to G. Okay, so this could also be defined inductively. So I could define G1, sorry, I should make it K plus 1 to make things, pardon me. So you could define G1 in terms of plugging in one vector, and then you could define GK plus 1 in terms of GK in terms of plugging in one vector. But anyway, let me not belabor that. Okay, and so G is called finite type if G GK equals 0 for sufficiently large k. In other words, if there is some L so that GK equals 0 for all k greater than L. And so let me just show you G1 for ON. Okay. So O, N, 1. Okay, so these are symmetric two forms. So these are tensors of the form lambda ijk. Let me call them B to be particularly suggestive. So B, I, J, K. Okay, so these are the coefficients. Okay, and they satisfy. Well, they should be symmetric in J and K. But on the other hand, if we plug in to either slot, we should get something skew symmetric. Okay, so they should also satisfy B I J K equals minus B J I K. Okay, so this is the expression of belonging to Sim2 Rn Rn. And this is the expression of giving something skew symmetric when you plug in for one of the inputs, okay, when you contract one of the inputs. All right, and the content of Cartan's lemma was verifying, or the uniqueness part of the Cartan's lemma was verifying that this is 0. Okay, so that any symmetric 2-1 tensor with these symmetries is trivial. And so, well, then I'll just tell you, but I'll pick up here next time, that a G structure of finite type is a reduction of the frame bundle to a linear group G, which is of finite type, whose Lie algebra is of finite type. Okay. And the significance of that is some version of the existence of this connection that I'll also talk about next time.